Welcome to Module 8.2. One of the first things we do when we first start playing with a program like Photoshop or similar is learning how to translate, resize or crop an image. The simple image manipulations can be described in terms of operators called affine transforms. The only problem is that affine transforms are defined for the continuous space, whereas here we are in discrete space. So in order to get the subpixel values that affine transforms require, we usually employ local interpolation schemes. And one very popular interpolation scheme is called the bilinear interpolation, and we will study how that works. Hi, and welcome to Module 8.2 of Digital Signal Processing. We will talk about image manipulations, and in particular we will consider a class of transformations called affine transforms, and we will see how to implement affine transforms for the class of digital images using the bilinear interpolation method. An affine transform is a mapping that reshapes a coordinate system. In our case, we're talking about images, so we're interested in a mapping from R2 to R2. An affine transform is defined in terms of a 2x2 matrix and a translation vector. And the new coordinate pair is given by the multiplication of the matrix times the original coordinate pair minus the translation vector. In compact form, we will express it like so. Let's look at some examples of affine transform. A very simple one is translation. The matrix here is the identity matrix, and the translation vector specifies the new origin of the plane. So if we have the simple image here and we apply a translation, we would get this simple result. Scaling is an affine transform where the matrix is a diagonal matrix and the diagonal entries are the amount of stretching or contraction of each axis independently. In this example, for instance, we have a scaling where clearly A1 is equal to A2 and both are less than 1 because the resulting image is larger. Rotation is another affine transform. We have seen this before. The structure of the matrix is like so. We have cosine of theta on the diagonal and sine of theta and minus sine of theta on the antidiagonal. A pure rotation leaves the origin in place. And as an example, here is a rotation by an angle theta that is clearly larger than pi over 2. And here, for instance, you have a rotation by pi. Flips can be both horizontal or vertical, and they simply swap the direction of an axis. In both cases, the matrix is diagonal, and in the case of a horizontal flip, the first element of the diagonal would be -1, and the second one is 1. Vice versa, for a vertical flip, the second axis gets flipped, and so the second element of a diagonal would be -1. Here in the image we see horizontal flip. Shear is a stretching of the plane in either the horizontal or vertical direction. For this case of affine transform, the matrix is either upper triangular or lower triangular. You have ones on the main diagonal, and according to whether the shear is horizontal or vertical, you have a parameter S on the upper corner or on the lower corner. The effect of shearing is like so. In this case, you have a horizontal shearing where the horizontal axis is stretched. If we now try to apply an affine transform to a digital image, we run into a fundamental problem. Remember, a digital image lives in discrete space. In other words, pixel coordinates are pairs of integers. They live in Z2. The affine transform, on the other hand, maps this original coordinates onto a point in R2, which means that the new pair of coordinates can lie anywhere on the plane, and in particular, it will most likely lie in between integer pixel coordinates. To understand the situation better, if this is the regular grid of pixels in Z2, and this is the result of the affine transformation, we would like that each point here on this grid be mapped to a point on this grid here. But unfortunately, the affine transform will probably map this point here in between. So how do we solve this problem? The first step is to consider the inverse transform. So instead of going from the original image to the destination image, here we draw it again, we start from the destination image, for which we know we want points to lie on the grid, and we compute the originating point from the original image. So if this is the original image, this is a transformed image, we take each point on the grid, and we find the point it would come from with the inverse transform. Now, just like before, this point will not lie on the original grid. But here's the second step. This pair of coordinates that we found with the inverse transform, we will express as two integer coordinates, eta 1 and eta 2, plus two correction factors, tau 1 and tau 2, where tau 1 and tau 2 are strictly less than 1. So it is a subpixel correction factor. So again, if this is a magnifying view of the original grid, our transform gives us a point here. We will find that this point t1, t2 is equal to a point on the grid, eta 1, eta 2, plus a correction factor tau 1 here, and a correction factor tau 2. So the question now is how to find the subpixel value here in the middle of the grid. And the idea is to interpolate from the four neighboring pixels. When the interpolation scheme between neighboring pixel is the linear interpolator, this strategy goes under the name of bilinear interpolation. So let's see how this works. We have our reference point, x of eta 1 and eta 2, and we also have the three neighboring points, like so. Remember, our subpixel value, as computed before, falls here in the middle, and it is expressed as a pixel at a horizontal distance of tau 1 and a vertical distance of tau 2 from the reference coordinate eta 1 and eta 2. So to compute its value, we first interpolate in the horizontal direction, and we find two subpixel values at vertical coordinate eta 2 and eta 2 plus 1, both at a distance of tau 1 from eta 1. And then once we have these two values, we compute a vertical interpolation at a distance of tau 2, like so. And this gives us our desired value. With a first order interpolator, the value is simply a linear combination of the values of the four pixels that we saw before, weighted by some factors that take their distance from the reference point into account. One thing that can happen is that when we compute t1 and t2 as the inverse affine transform, we get a value that falls outside of the support of the original image. And in that case, we will have to replace this value with the standard value of choice, which is usually 0. We can now try and use the bilinear interpolation to compute the sharing of a standard image, and if we do that, we obtain something like this.